Hello viewers, in this video I will guide you how to draw the SFD and BMD diagram by using the equation method for this type of loading. The graphical method for drawing the SFD and BMD diagram is the simple method, easy one, but sometimes you need the equation method. It is necessary for you to learn this method. In case of complex loading, complex UVLs, I will tell you further in this video where you can need this, which are the situations where you will need the equation method. These are my reactions that I have find out here. This is VE and this is VA. You can see my another video for reaction. I have explained it in detail. For SFD and BMD diagram by equation method, we will make the equation for this region and for this region and take this distance as x and for this region. So we will make the different equations for these three regions because the loading is changing in these three regions, and in wherever the loading is changing, you will make the separate equation for that region and solve it furthermore. And first of all, I will make the equation for this region, cut it from here and take this distance is x. And this is V1 shearing force acting at this face which we have cut. And this is moment acting at this face. Shear force equation. Sum of all vertical forces equal to 0 and the force acting upward taken as positive and acting downward taken as negative. V1 is acting downward, so taken as negative. 2 into x is the UDL force acting downward taken as negative, and VA is 11.67 acting upward taken as positive. So their sum is equal to 0. As I have said earlier, the summation of all vertical forces equal to 0. The V1, arranging this equation, I will get this equation. This is my final shear force equation for this region. If I take x is equal to 0, mean at that point I will get the V value, which is 11.67 is equal to VA. Okay, this is my V1 value, and if I put x is equal to 5 at that point, x is equal to 5 at B, I will get V2 is 1.67. and in this region, this is the SFD drawn in this region. This equation can be used for only this region. If I want to find out the shear force value at any point, at here 1 feet, from here 2 feet or 3 feet, I will put simply that value, that distant value here in place of x and find this shear force at that desired point. So this is the use of equation. This can be used only for this region. And now I will draw the equation for bending moment equation. For this I will take the moment about point P1 and take counterclockwise moment as a positive. Taken M1 as a positive because it is counterclockwise. Taken 2 into x is the UDL force value, and x by 2 is its moment arm about point P1, and 11.67 into x is the moment value acting. This create the clockwise moment. This 11.67 create the clockwise moment about point P1, so take as it as a negative. So is equal to 0 because the summation of all the moments equal to 0. These three moments acting in this case. If I take moment about this point, this M1 acting counterclockwise, 2 into x force create counterclockwise moment about P1, and 11.67 force create counterclockwise moment, clockwise moment. This create clockwise moment about P1. arranging this equation, I will get this equation. So this is now my moment equation for this region, and in this region I put any value of x from 0 to 5. I will get the moment value for at that point. In this equation, putting x is equal to 0, I will get m1 0, and in this equation putting x is equal to 5, here at b point I will get m2 value 33.5. Drawn this curve like that. So this equation can be used only for this region. Now how this curve is drawn, I will explain you it now. This is my, for this region, SFD drawn and BMD drawn. Now how these lines are drawn, how this curve is drawn, this I will explain you now. The slope of SFD line is actually the loading behavior, is depend upon the loading behavior, and the slope of BMD line, this is the slope of BMD line, is depend upon SFD behavior. Now see how the loading behavior is. The load here, the UDL load for this region is constant and downward. So slope of SFD line will be constant and negative. It is equal to this value. It is constant, and due to downward loading value it is taken as negative. So the slope of SFD line will be constant and negative. Its slope is constant, it is constant slope line, and it is downward. From this point it is downward, so taken as negative. So this is how the slope of SFD line should be taken. Now I will explain you the slope of BMD line. Slope of BMD line is equal to the SFD behavior. How the SFD behavior is? SFD is decreasing and positive. We move from here to this point, the SFD is decreasing. Here the SFD value is 11 and here it is 1.67. So it is decreasing as we move here. From left to right it is decreasing, and it is positive because it is above the baseline. So the slope of the BMD line will be equal to SFD, which is equal to decreasing and positive. So this slope will be decreasing and positive. How it is decreasing and positive, I will explain you now. These are the some four possible curves that you will draw in BMD, that you will face in drawing the BMD line. Here I have drawn decreasing and positive line. How I get these terms? I get these terms from this SFD value. Now this is the decreasing and positive line which I have drawn here. So this is the positive and decreasing and positive line because it is up above this my baseline, so it is positive, and it is decreasing. Here you can see the slope is higher, the slope is low, the slope is 0. So the slope is decreasing as we are moving from left to right. From left to right the slope is decreasing, and it is above the baseline, so it is positive. Here it is also, in this case, also above the baseline it is positive. Here it is below the baseline it is negative, below the baseline it is negative. So now the positive and negative scene is clear, and now I will explain you decreasing and increasing. Here the slope is also decreasing because here the slope is, as we moving from left to right, the slope is higher, lower, and it is 0. And in this case the slope is increasing. Here the slope is 0, the slope is increased, and the slope is increased as we move from left to right. Also in this case the slope is increasing. So these type of curves you will face while drawing the SFD and BMD diagram. And remember one thing more, the slope of SFD line will be 1 degree higher than the slope of loading acting over here, and the slope of BMD line will be 1 degree higher than the slope of SFD line. Here the slope of the loading is 0, it is constant straight line, it is 0, and its slope is 1 degree line, first degree slope constant, and it is second degree line, so this is how the BMD and SFD should be drawn properly. And these are the few examples that you can see here. This is the 0 degree line. Here the no loading acting, no UDL UVL acting, so here the SFD, their SFD will be 0 degree line and their BMD will be first degree line. And in this case you can also see the load is acting over here, so it is the 0 degree line. Slope of loading line is 0 degree, and here its slope is first degree, and here its slope is second degree. You practice it furthermore. Now let's proceed to our beam. This is my shear force equation and this is my bending equation for this region. Now I will proceed for this region. I will cut it from here, take this distance as a x and make the equation for this region, for this 5 feet span. Similarly the shear force and moment act at this face which we have cut it, and this distance is taken as x. Shear force equation, similarly the positive force, downward force taken as negative and upward force taken as positive, and the summation of vertical force is equal to 0. V2, this one force is acting. V2 is this one. 2 into 5 is this UDL force acting downward, and 11.67 is the reaction acting upward. And arranging this equation I will get V2 is equal to 1.67. In this region the shear force value is same, constant, which is equal to 1.67. It does not depend upon x value as it was in previous case. This equation exists for this region. Now I will draw the equation for bending moment for this region. I will cut it from here, and this is my bending moment acting over here, taken it as a counterclockwise always for the first position, taking moment about point P2. This is my point P2 and taken counterclockwise moment as a positive. M2 is acting counterclockwise, taken as positive. This 2 into 5 is the UDL force, and 2.5 plus x. This is the half of this 5 plus x. This is the moment arm about point P2 for this UDL. So taken as positive because this also create counterclockwise moment about point P. And 11.67 is the reaction. This create clockwise moment. So taken as negative, and into 5 plus x is the moment arm. 5 is this distance and x is this distance. This is the total moment arm of 11.67 reaction about point P2. Arranging this equation, I will get this final equation for this region for the moment. And if I put x is equal to 0 at this B point, I will get the moment at B point, which is 33.35. And if I put x is equal to 5, I will get the moment value at point C here, which is 41.7. This is BMD for this region, and this equation exists only for this. This is BMD for this region, and this equation exists only for this. Really cut it from here and make the equation for V3 for this region and draw the SFD diagram as I have drawn previously. And now for this region I will make the equation for moment. Similarly, taken moment about P3. But now this is my M3, create the counterclockwise moment taken as positive, and this is my 10x. This 10 is the concentric load and x is the moment arm, create counterclockwise moment about point P3. We are taking moment about point P3, and this is the UDL value, force, and this is the moment arm. Half of this 5 plus 5 plus x is the moment arm, and this is the reaction. 11.67 multiplied by 5 plus 5 plus x is the moment arm, taken as negative because this create the clockwise moment about point P1. And arranging this equation, I will get this equation for moment for this region. Putting x is equal to 0 in this equation, I will get moment value at point C, because x start from here. X0 value is at point C, I will get this moment value, and putting x is equal to 5, I will get m3 is equal to 0 at this point. The m should be 0 at pin and roller. This is how the BMD can be drawn by using this equation for this region. So these are the few examples for your practice. This is the UDL case and this is its equation. For this UDL case, no loading is changing for this 20 feet span, so we will have one equation for shear force and one equation for moment for the whole span, and using this equation you can draw this SFD, and using this equation you can draw this BMD. In this video I will explain you how we can draw the shear force and bending moment diagram by using the equation method when UVL is acting on the beam. These are my reactions that I have found out. You can watch my another video how we can find out the reaction. In description I have given the link for that video. For making the equation for the shear force and bending moments, what I will do, I will cut the beam from here and take this distance as a x. The shear force and the moment are act at that phase which we have cut over here, and take these directions as they are. If we cut it from here and take the left side, then we will take these directions opposite. So now I will take these directions as they are because I am taking the right side. And now I will take the shear forces equation. Sum of all vertical forces equal to 0. The force which is acting upward taken as positive, the force which is acting downward taken as negative. V is acting upward over here. Only for this region I will apply the equation over here. The V is acting upward taken as positive, the 2x divided by y. This is the UVL acting downward taken as negative, x into y divided by 2, because this UVL area is actually the force acting downward. And this 16.67 is the reaction over here acting upward. These three forces are acting at this phase which we have cut. This V1, this UVL downward, and 16.67 upward, their sum equal to 0. Now how we will find out this y? We can find out this y by the slope method. How the slope method is, this 5 value total and this total span is 20. Dividing 5 by 20 is equal to, this value will give us slope value is equal to y divided by x. This is how we can find out y is equal to 5x divided by 20. This 5 divided by 20 over here must be equal to y divided by x over here. So this is y is equal to this one, and put this y in this equation, I will get this equation. Arranging this equation, this is my shear force equation for this UVL. Throughout the span, the one equation will exist for shear force. This is my equation. How we will draw the shear force diagram by using this equation? I will put simply x is equal to 0 at that point and get the V1 is equal to this value, this, and I will put the x is equal to 5 somewhat over here, and I will get the shear value at x is equal to 5 somewhat over here, somewhere over here, and this is my x is equal to 5, the shear value at that point. And I will put the x is equal to 10 and get the shear value at x is equal to 10. This is my shear value at x is equal to 10 at midpoint, and then I will put the x is equal to 20 over here. What is the shear value? It will be 33 positive, and this is my shear force diagram for this UVL acting over the beam. So this is how you can draw the shear force diagram by using this equation. By putting simply different distances of x, and you will draw the shear force diagram. Now the question arises that find this point where the shear force is 0. The shear force is 0 at that point. I will find out this point because this point is we will need this point in further. This question can also be arises in the question paper or anywhere you can need this. I will simply put shear is equal to 0 in this equation, and I will find out x distance is equal to 11.5, and this is my x distance where shear is equal to 0. And this is my equation for the shear for this UVL, and now I will make the equation for bending moment. For bending moment, take the moment about point P1. This is my point P1. I will take the moment about that point and take counterclockwise moment as positive and clockwise moment as a negative. This is my M is clockwise moment about point P, so taken as negative. And this 16.67 is the force, reaction force acting upward multiplied by X. X is the moment arm about point A for this force, and taken as positive because this force creates the counterclockwise movement about point P, this point. And then the UVL here, the UVL force is xy divided by 2 and multiplied by x by 3 is the moment arm of this UVL about point P. This is also taken as negative because this create this clockwise movement, like this clockwise movement about point P, so taken as negative. Its sum is equal to 0. Now how we will find out the y? We will find out the y by same method as we have find out previously by slope method. And this is my moment equation for this UVL. Using this moment equation, we will draw the bending moment diagram by same method. Putting x is equal to 0, we will get moment at that point. Putting x is equal to 5, we will get moment at distance 5. Putting x is equal to 10, we will get moment value at distance of 10. And here we need this distance where the shear force is 0. This is the distance where shear force is 0. At that point there will be maximum moment, so that is why we need the point where the shear force 0. I have said you earlier. The 128.34 is the maximum moment for this beam when the UVL is acting over there of this value. Okay, then put x is equal to 20. I will get this moment over here. At the roller and pin, moment must be 0. This is the BMD diagram I can draw by this method using this equation. This is my SFD diagram by using this equation I have drawn, and this is my BMD diagram I have drawn using this equation for this type of UVL acting over 20 feet span. And this is my another type of beam for different loadings. Here the only one type of loading was acting over the beam, so I have taken only one equation for the SFD and one equation for the BMD for drawing them. And now here the three regions are over here because the load is changing, so I will make the three different equations for these regions and then draw the SFD and BMD diagrams for the respective region. This is the equation. This is the example for your practice. You can make it as your practice. And this is the shear force and moment equation for this region only. And you will get in this region the shear force and bending moment values only for this region. And these V2 and M2 are the equations only for this region. You will get these values, these shear values by this equation, these moment values by this equation. And in this region you will get this M3 and V3 is the shear force equation and M3 is the moment equation. And you will apply only these equations, shear force equation for this region and bending moment equation for this region, for drawing this region. This is the example. You can practice it at your own job, and for any query you can consult with me. You can comment, or you can